Hello, in this video we're gonna see basic set identities. For example, if we have set B and C, and universal set S, and a null set in the empty set, and we have these properties. The commutative property holds here. A union B is the same as B union A. And A intersect B is the same as B intersect A. The associative property is the same as A union B. B union C is the same as A union B union C. And the associative property, A union B union C, so you could move the parentheses. This is the same for addition, for example. It's the same as for addition. 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. And as we've seen before, set identities are very similar to the logic that we've seen in chapter 1. For example, A or B is the same as B or A. And the same when we have A and B and C is the same as A and B and C. So in logic, what we use or is a union within set, and become intersection. And the all properties. The other thing is that when you have distributive property, and logic is the same as in here. As you could see, if you have A intersect B or C, there will be A intersect B or A intersect C. And the same way, when you have a union, then you'll do B, then you do A or B intersect A or C. So I say or union because they are similar. The other thing is the identity. So an empty set, union A, what's union with A? An empty set. So an empty set union A is the same as A union empty set, which is the same as A. So you get the identity A. So for set, when you have union, the identity will be an empty set. For example, if you have an addition operation, what would be the identity for addition? X plus what gives me just X? That will be 0 here. So if I have multiplication, X times what gives me just X? 1. So here we say 1 is the identity for multiplication and 0 is the identity for addition. So for the union, empty set is the identity. And to relate this with the logic, so empty set will be false. So false or A, that will be A. And the same A or false will be also A. In this case here, S is universal set, everything. So S intersect with A is the same as A intersect with S, which is A. So compare this with the logic, S would be true, always true. So true and A, that will be A and true also will be A. So the complement property, we have A union not A, that will be S. And you could picture, if you have A here, everything else is not A. So the union between A and not A, that will give you the whole universal set S. And what's common between A and not A is an empty set S. And again, to relate this with logic, A or not A, that will be true if you do the truth table. So as we've seen before, the truth table, A can be true or false, not A, false or true. So A or not A is always true is a tautology. So as we said, S represents basically that tautology, always true. And empty set represents false. Because as we see here, A intersect not A is empty set. In logic, we said A and not A is a contradiction. So as we continue here with this, if I say A and not A, that will always be false, which is a contradiction. So here I just want to relate where we see here within a set is the same concept and the same identities as we've seen with the logic. Remember, union is or, intersection is and, empty set is false, contradiction, and universal set S is tautology is S. So in the same thing with the double negation, we call it before. When you double negate, you go back to A. Idempotent, as we've seen before, which is the mode that affirm in Latin, which is A, or A is just A, as we've seen before. A and A is just A. And the absorption, A or A and B is A and A or B is A. You could prove this by using distribution. And the set difference, as we call it earlier, A but not B, you could write it as A intersect not B. Inclusion in union, I mean A, it belongs to A union B because it's part of the union. And B is also belongs to A union B. So the inclusion in intersection is that the intersection between A and B. So if you have an intersection of A and B right here, so this intersection A and B, assume this is A and this is B. So this part intersection of A and B is part of A, and also it is part of B. That's why it belongs to A and belongs to B. And transitive property of subset, I mean if A is part of C and B is part of C, therefore A must be part of C. It's like one within the other. A, so B is within A and C within B, therefore C gonna be within A. Let's see these two examples. We need to prove that A intersects C, but not C and not B is the same as A intersect B intersect C. So we're gonna start with one side and try to get to the other. And it looks like it's easier to start with this side. So what we have here is A intersects C, not C, not B. So if we use the set difference, we will have A intersect C, not C intersect B, not. And it looks like we could use the set difference again for this not. We make it intersection and we negate the second part. And now it looks like we could use the Morgan's law. The Morgan's law in logic applies here as well. Negate C and change intersection to union and negate not B. Now it looks like we could use double negation here for B, B. So right here I could see that we can use distribution, meaning I'll take this union C naught and then union B. And it looks like we could use associative law right here at the first term here. So what we're gonna have is A intersect C and not C. Keep everything the same on the other side. And now we know that C intersect with not C is an empty set. It's complement here. And now A intersect with an empty set, it's just an empty set. This is the intersection with empty set. Every time you intersect with an empty set, you get an empty set. So the next thing is, again, the identity, because I have union, empty set, and empty set, union, anything is the same thing because of the identity. Then I will use the associative law, and one more time commutative law, and then one more time the associative law, and we're done. We end up with the right hand side. Let's see another example here. So I have A union B but not C intersect with B not. I need to show that this is the same as A but not B. So we start with the left hand. So what I'm going to use a commutative law. I need to start with not B intersect A union B but not C. So after this we're going to do the distribution not B with the A. Here is one. Union, because of this is connection between the two. Union not B A B but not C. Not B intersect B but not C. So I see like we could use the associative law, not B and B. So right here I could use set difference, B intersect not C. for this. B but not C is the same as B intersect not C. And now not B and A union, I use the associative law right here. So we know that B and not B is an empty set, intersect with not C because of complement. And now intersection with any, and now intersection between not C and empty set is just an empty set. This is because intersection with empty set is just empty set. And now the union with an empty set is the identity property, which is just gonna give me not B and A. So here I stop and think, but what I need is A but not B. So what I'm gonna do is commutative first, gives me A intersect not B, and then I'm gonna write it as the set difference, which is A but not B, which is equal to the right hand side, and we're done. And this is how we prove set using identities.